All right, let's start section 2.2, part 1. We're going to talk about polynomial functions, and this is a pretty important topic. You've actually talked about this in many of your classes up to this point because it's a really important topic. So let's continue it with concerns to pre-calc and calc. So the essential question we're trying to answer is, what are polynomial functions and how do we graph them? All right, we're not going to quite get to the graphing part today, but we're going to learn about polynomial functions. So what we're going to learn how to graph, but we're going to learn the different characteristics of graphing, okay, first. So we're going to learn about the characteristics. The actual graphing part will be in part 2 of section 2.2. All right, so here we go. What is a polynomial function? A polynomial function are sums or differences of monomial functions. Monomial meaning one term. So basically a polynomial is a bunch of one terms being added or subtracted together. Okay. So here is the fancy math lingo equation for polynomials, but basically all it says is that you start with the leading coefficient, and whatever your exponent is, that it should go in order in standard form. So plus or minus, you could have 6x to the fourth minus 4 x to the third minus 6x squared. So notice that the exponents are going down 1 every time. Okay, you don't necessarily have to have all of them, but if you do have all of them, it should go in order: 5, 4, 3, 2, 1, and then 0. All right. So we have actually talked about some polynomials so far this year. The polynomial that starts off with 0 exponent, x to the 0 plus c, we learned that those were called constant functions. Okay, that is a polynomial when x is equal to 0, or your exponent is equal to 0. When your exponent is equal to 1, this is actually called a linear function, and this is diagonal straight lines. And then last but not least, when your exponent is 2, remember we had things called parabolas, okay, and those were called quadratic polynomials. All right, so we've learned about constant, linear, and quadratic. Now we're going to talk more about cubes and quartics, so degree 3 and degree 4 polynomials. All right, so just some random general things about polynomials. Polynomial function graphs are always continuous and have smooth, rounded curves. So what it's saying is polynomial function graphs never have gaps, holes, breaks, or sharp corners. So if we look at this one, you notice there it's continuous, it's not ending, it has rounded curves, there's no gaps, there's no breaks, my pencil doesn't have to leave the page. Okay, it's a very nice curved, no sharp corners graph. All right, so that's what most polynomials look like in one way or another. All right, so let's recall from section 2.1 that when your polynomial function has an even degree, okay, your graph is probably going to look like this or like this. So both ends going up or both ends going down. If it is an odd degree, so this, for instance, x squared or x to the third odd degree, one end is going to go up and the other end is going to go down. Okay, and you could also go the opposite direction. One end goes up, one end goes down. Okay, so that's when you have an odd degree. So that was from section 2.1. All right, so let's specifically talk about this idea of end behavior for polynomials. All right, so we have this chart from the book, and it's a lot of stuff here, but basically this is what you need to know. When your n is odd, so remember n is the exponent. So we have an odd exponent, for instance, x cubed, and our an, and notice an is the leading coefficient. When our an is positive, so let's just say 4x to the cubed, the right side is going to go up and the left side is going to go down. Okay, that's basically what it's telling us. And then this one on the right here, when your n is odd, so remember n is your exponent, so when n is odd, let's do cubed again, and your an is negative, so let's do negative 4. Kind of squish that together, sorry, so that says negative 4x cubed. The left side is going to go up, and the right side is going to go down. Okay, so that's when your n is odd, and your a is positive, a is negative. Okay, that's what the graph is basically going to do, and it's talking about end behavior here. Now, vice versa, if your n is even, so x to the fourth, and it's positive, so 4x to the fourth, they're both going to go up. The left and the right side go up. And the opposite is if your an is negative, so negative 4x to the fourth, they're both going to go down. Okay, so that's what this chart is kind of talking about. And this holds true for all of these polynomials. They have these specific characteristics. All right, so let's look at here. Let's see what we have here. It says describe the end behavior of each graph using polynomial function using limits. Okay, so we're going to do the limit as x approaches infinity. What's our function equal to? And we're going to do the limit as x approaches negative infinity. What does our function do? Okay, so let's do this in terms of our a and n. So this is called the leading term test. All right, so let's see here. So remember, a is the leading coefficient. So what is our leading coefficient? Our leading coefficient is 3. Okay, so that's positive. And our n is 4, so that is even. So we have a positive and we have even. Okay, so positive and even. So even and positive. Our graph should look like this right here, where both the left and the right go up. So the left goes to positive infinity and the right goes to positive infinity. So the right side of my graph, the one that goes to positive infinity, should also go to positive infinity, and the left side also goes to positive infinity. So let's see if that's true. So what I did on the bottom here is I graphed this on my calculator, and we can see that the left side goes to positive infinity. So as x gets bigger, my graph goes up, and as x gets smaller, my graph also goes up. So that is true. The leading test worked for this one. All right, let's go to the next one. All right, so here's a new equation, same exact question. Our number in front is a -3, so that is negative. And we have a even power of 2, so that is even again. All right, so let's see here. So negative and even. So n is odd, even, negative. Okay, so it should look like this. They should both go down towards negative infinity. Let's see if that was true. So that one. All right, now I think I might have, oh, my fault. Okay, so what we need to do is I got sucked into here. I read the problem wrong. Okay, so what do I notice? Hopefully you notice what I didn't notice right away is this is not in standard form. We have to use the biggest exponent to go in front. Okay, so if I put this in standard form, now I can do the problem. So my a is -2, so that is negative. And my n is 7, so that is odd. Okay, so odd and negative. Odd and negative. So odd, negative. Okay, so my left side should go up and my right side should go down. So let's see. So limit as x approaches infinity, my function is equal to, let's see, as x approaches infinity, so as my graph goes to the right, look, my y goes down, so it's approaching negative infinity. And as the limit as x approaches negative infinity, so as my x goes left, my graph is going up. So f of x is going to positive infinity. So my leading test worked again. Okay, so here are the answers. All right, so those are the limits for my end behavior. All right, so typical cubic and quartic functions. So cubic means x to the third. Okay, so we have sideways s's here. All right, so and then depending on what your a value is, we have our end behaviors. All right, now, but let's look at here. And then quartic, sorry, we have quartic, which is x to the fourth. These are w's or m's. All right, so let's see here. Turning points indicate where the graph of a function changes from increasing to decreasing or vice versa. So let's label where our turning points are. So we're decreasing, there's a point here, and then now all of a sudden we're decreasing. So there's a turning point. So we're increasing, increasing, increasing. Oh, we come to a top, and then we're decreasing again. So same thing. So cubics have 2 turning points. Quartics, how many do these have? So we're decreasing, we get to a point, we're increasing, get to the top, decreasing. So x to the fourth have 3 turning points. Okay, so cubic has at most 2 turning points, quartic has at most 3 turning points. All right, so hopefully that makes a little bit of sense. And notice how many, oh, we'll talk about that later. We'll talk about x-intercepts later. All right, so zeros and turning points of polynomial functions. All right, so a polynomial function f of degree n greater than 1 Okay, so this one is actually x to the 6th, has at most n, so whatever the highest exponent, so if you want to write this down, highest exponent is the most zeros it can have. So this one is a degree 6, so the most it can have is 6. 6 distinct real zeros. All right. If you take the highest exponent and you subtract 1, that is how many turning points? Number of turning points. Okay, so if we take 6 and we minus 1, we can get 5 maximum turning points. Now, does it have to have that many? No, but this is the most it can have. Okay, so these are the most it can have. Okay, so let's look at what the graph has of this one. Okay, so let's see, count the number of zeros. Okay, this one has 1, 2, 3 zeros. Okay, it can have 6. It can have 6, but it only has 3, which is okay. How many turning points does it have? 1 down here. Use a different color, so it has 1 down here, 1 at that 0, and then 1 down here. So it has 3 turning points. Now, it can have 5, but this one just happens to have 3, which is okay. Okay, so but that it can have whatever the exponent is, that's how many zeros it can have, and what the exponent is minus 1, that's how many turning points it can have. All right. So it says state the number of possible real zeros and turning points of x cubed minus 5x squared plus 6x. Okay, so it is a degree 3, so it can have 3 real zeros. Okay, and it can have 2 turning points because it has a degree 3. So 3 minus 1 is 2. Okay, now that's what it can have. It doesn't necessarily have to have that, but it could. And then it says determine the number of real zeros by factoring. So we're going to factor x cubed minus 5x squared plus 6x equals 0. So we're going to factor this. All right, so notice x cubed minus 5x squared plus 6x, I can take out an x. So when I have take out an x out of x cubed, I have x squared minus 5. I took 1x away, so 5x plus 6 because I took this x away. All right, so let's see here. So we have x, and now I can factor this standard quadratic, x and x. All right, what two numbers multiply to be 6 and add to negative 5? Hopefully you see that negative 3 and negative 2 multiply to be 6, but add to negative 5. All right, so I have 3 answers. Okay, my 3 zeros are 0. Remember, you switch the sign, so positive 3. And remember, you switch the sign, so positive 2. So there are my 3 real zeros. I factored it. All right. And last but not least, we're going to do the same exact thing for x to the 4th. Okay, so let's actually, what I want to do is I'm going to do these last 2 in class with you. So I'm going to do this x to the 4th with you in class, and I'm going to do this x to the 5th. But let's answer the first question. How many possible real zeros can I have? Possible real zeros. Okay, it's a power of 4, so it can have at most 4. Okay, turning points. Okay, you take your zeros minus 1, so it can have at most 3 turning points. Doesn't have to have that many, but it could. Okay, and then we'll factor this one in class, and we'll factor this last one in class, and then we will be done with section 2.2 part 1. Have a good night, and I'll see you tomorrow.